Okay, so today we're going to finish up with searching and sorting by reviewing what we've been doing so far with the films that we've been working with, like you worked with the teams structure that you had yesterday in your lab. And then, of course, in your hack this week, you will be working with, I believe, the airports again. And you'll be, be defining some comparators there, searching and sorting features as well. All right. So, and then it's not going to take us the entire time. So what I want to do at the end is start with a completely new problem and show you how searching and sorting is fundamental to solving that problem. And that'll help you also with your project after the break. By the way, if you haven't already, make sure that you are reading the Piazza posts. There's a hack resubmission opportunity. There is additional information on how the rest of the semester will go, including stuff on Lab 14, etc. All right, so we left it off last time by making these two comparators, the CMP film by title in ascending order, CMP film by director name. That one was done by their last name and then their first name. So if you had two directors with the same last name, then like Smith and Smith, then Alan Smith would come before Berta Smith or something like that. So I've went ahead and created a few more movies here. In fact, 9 movies in total here. And I'm printing them out. And then we're going to go ahead and play around with this and do some more comparators or whatever we want to do here. So if I'm going to go ahead and print out these films, I'll go ahead and compile everything together here first. Demo.c. Remember that we are online, so if you have any questions, please go ahead and post to Piazza or go ahead and post to the YouTube chat. They're both up. So let's go ahead and just print this out. And I made some updates here so that it's a little bit more readable. But there are the titles on the left-hand side. There are the ratings, and then there are the directors, last name, comma, first name. Okay. So what I want to do first is utilize these comparators. CMP. Let's go ahead and sort them by the title in ascending order. Okay. So first of all, I'm going to call. Should I call my own sorting algorithms? No, you learned yesterday in your lab that that's not the proper way of doing it. Instead, you use QSort. Now, QSort takes 4 arguments here. What are those 4 arguments? The thing that you want to sort, in this case, ARR, right? The number of elements in that array, and I put that into a variable called n, right? And then finally, and then the third one is going to be the size of each element in that array. Well, each element in this array is a film, so how do I know how many bytes a film takes? Size of? Oh, so it's not 10 here because first of all, there are 9 films in it, right? But each one of them takes size of film, right? If we were to remember that when we actually created one of these things, say in create film, how did I call malloc? You want one film, how many bytes does a film take? Size of film. Because it's a user-defined type, the compiler is able to go in and count this stuff up. Okay, the double, that's 8 bytes. 2 pointers, that's probably 16 more bytes, so 24 total here. Oh, and a person? Oh, a person is another 16 bytes of pointers. Oh, and it's also a date. Okay, well, a date is 3 integers. That's going to be 12 bytes right there. It's able to add all that stuff up, and you don't have to worry about it, right? So there's the size of film. Finally, the last argument is the comparator that you want to use to sort. In this case, I called my sorting algorithm what? Or my comparator CMP film by title ascending. And I pass that in by giving it the name of the function that I want it to use. The name of the function that I want it to use is also its memory address. Just like the name of this array here is already a memory address, right? I don't have to use the ampersand in front of it. You can if you want to for this, but why? Right? All right, let's go ahead and make sure that it works by printing them out a second time. When I compile this stuff, and actually let me go ahead and print out a blank line as well, printf, well, here, a nice pretty, not like that, but a nice pretty demarcation right there, right? You can get into ASCII art all you want. and make it look as pretty as you want if you really want to. But I'll just go ahead and print it out like that. All right? Now, when I run this, here's the original order, just like you saw in your lab yesterday. That's just the order that I put stuff in. Now down here is the order of these films. It went in order of ascending order with respect to their title. So of course, Arrival is going to be first, and then we've got Bad Lieutenant, then Blade Runner. We've got 2 copies of Dune here. One of them was directed by Denis, and the other one was directed by David. Right? Which one comes first? Which one comes first according to this? That's a tie. Right? Break ties arbitrarily. Q-sort will look at this and say that this Dune and this Dune, from the perspective of this comparator, they're the same thing. So they're in order this way, they're in order this way. I'm just not going to swap them, right? Whatever order you're rolling the dice. It could end up swapping them. It could end up not swapping them. That's something called sorting stability. Originally, how did I have this? Let's see. Denis' Dune here was first, and David Lynch's Dune was second when I was in the original array. And looks like that order was ultimately preserved, right? The original Dune, the first Dune was here, and the second Dune was here, and that's the order that they stayed in. That means that potentially that this implementation of quicksort is stable. It will not put things that are otherwise equal out of the original order. I don't know if it's stable all the time. We'd have to do a few tests here, maybe even look at the actual implementation to determine that. But that's another thing that you can get into with searching and sorting algorithms, stability. All right, what's the last one here? The wild blue yonder. Right? Typically, when titles of films or books or things like that are sorted, articles like the, an, right, they're ignored. In this case, though, I didn't implement that. Right? Why is this the last? Well, because it starts with a capital T. Right? If you want that behavior, that's going to be a little bit different implementation than what we have up here. How would you go about doing that? You would have to check to see if the title begins with a title, the, a, an, uppercase, lowercase, whatever, and then ignore it and make the comparison based on a substring somewhere else. A little bit more complicated logic if you want to, right? But for this, it's good enough. We'll go ahead and sort it by something else. CMP film by director name. Remember that it's last name, then first name. Okay? Let's go ahead and quick sort that again. Print it out again. I don't need this one now. There we go. And instead of using that comparator, let's go ahead and use this director name comparator. Run this again. And we'll see that Werner Herzog comes before David Lynch. Why? Well, because H comes before L, and then that's followed by V. Right? What about the original order here? Arrival, Blade Runner, and then Dune. That looks like it's the same here, so maybe it is a stable sorting algorithm. We've got Dune, Eraserhead, and Lost Highway. Was that the original for them? Dune, Lost Highway, Eraserhead. So the original order was not preserved. That means that this is actually an unstable sorting algorithm. Why would that matter? Think about it like this. Think about sorting by year, by say freshman, sophomore, junior, senior. And then you want to sort by GPA. So you want the highest GPA freshman, then to the lowest GPA freshman. Then you want the highest GPA sophomore down to the lowest GPA sophomore, etc. What if you had an unstable sorting algorithm? Would that original order have been preserved? First of all, you sort it by, the GPA, highest to lowest. Then you sort it by year, freshman, sophomore, junior, senior. Right? You would expect the high GPAs to the low GPAs to be preserved. Right? That's what you would want because you want it sorted by 2 columns, basically. But if it's an unstable sorting algorithm, there's no guarantee on that. You could have all the freshmen here, but then all of the GPAs are completely in different orders. Right? If you want to sort by multiple columns, you want a stable sorting algorithm. Unfortunately, this happens to be an unstable sorting algorithm. There's no guarantee on what otherwise equal items will end up being. So be careful. If you want, based on two things, for example, if you want director name and then you want the title, you would have to come up with yet another comparator. Let's do that. All right. So I'll call this comparator CMP film by director name, then by title, right? And what would that look like? I just cut and pasted this. We're going to have to modify it. Here, I'm doing director name, right? And I would capture this yet again. Result is equal to strcmp. So if the result is 0, then that means that they have the same last name. If the result is still 0 after comparing their first name, if result is equal to 0, then that means that they have the same first name, last name, and the same first name. In other words, David Lynch, David Lynch, David Lynch. If you want to then go to break ties by the title, then you would make a return strcmp of X's title compared to Y's title. There we go. Else, return the result. Let's go ahead and see what that looks like now. Cut, paste this. And what did I call it? Director name, then by title. All right. And we should see that Arrival Blade Runner Dune is still preserved there. Right? David Lynch is now Dune Eraserhead Lost Highway. And Werner Herzog is Bad Lieutenant, My Son, and the Wild Blue Yonder. Right? Is there a better way? That seems like a lot of code. In fact, a lot of repeated code from two different functions. What could I have done instead? Don't worry about that. Do a comparison by director name, right? Get the result of that, of A and B. Now, if that result is 0, then that means that they have the same last name and first name because that's what that comparator does. And if it's 0, then all I need to do is return a comparison based on the title in ascending order. Right? Return A, B. Else, return the result that you had before. Much simpler, right? Code reuse. This is why we do this. Right? And I think I'll get the same exact behavior as before. Let's just look at this. Bad Lieutenant, My Son, and the. Great. How else would you go about? Oh, what else do you want to see? I'll let you determine. How else could we sort films? So we've only been sorting by strings so far. Let's do one last one that involves the IMDb rating, right? Highest to lowest or lowest to highest. We want the best films, right? And then that's going to be our priority for watching these. By the way, these are just made up numbers. I don't know what the actual IMDb rating is, but they are all excellent films, so you should watch them all. I have not yet still seen the Denis Dune yet, though, so I can't actually say that. All right, so let's go ahead and compare them by, compare a film by, it's not rating like G, PG, 13, R, whatever, but by IMDb rating, IMDb rating. Oh, and this raises actually a good question on styling. So IMDb is an acronym. So should we do it IMDb all uppercase like this? Or it's an acronym, so we'll treat it as one entity, one word, and use lower camel casing on it like this, IMDb. Right? You can go ahead and have your holy wars as to which one is correct. I'll just go ahead and go with this. Right? All right, so I'm going to go ahead and typecast them as films. And then make the comparisons. So how do I get the IMDb rating of these things? X is, what was it called? IMDb rating, there it is. Right? And over here to demo. And by the way, most of this stuff should be going in the header files and the source files. I'm just doing this as a demonstration. Remember what happened when we tried something like this? Is this going to work? taking the difference. What's going to happen here? What if I had a 9.0 and a 9.5, or 9.5 and minus 9.0? What's the difference there going to be? 0.5. What happens when I return that as an integer? Truncates, and so I get that this is 0. In other words, the movie with a rating of 9.0 is exactly the same as the movie rating with 9.5. Nope. So don't do that. What order do I do this in? If X's IMDb rating is less than Y's IMDb rating, what should I return? So it helps to think about these by putting actual values in this. 10 and 9, right? So, or 9 and 10 in this case. 9 is less than 10. Are they in order or out of order? If you want the best films up here, the top rated films up here, and the lower rated films down here, is that in order or out of order? Out of order. And if it's out of order, what do you return? Something, remember, something negative, positive, or 0. So this should be positive 1. Right? Don't put that one plus there though. Right? All right. If it's not, then we can always come back and fix it. Right? So else if. Actually, yeah, I'll go ahead and do it like this. Else if X is equal, there we go, return 0. This is not the pattern I was following before, and for a very good reason. These are floating point numbers. So take 1 and divide by 3. What do you get? 0.3333333, and then at some point you add the representation and it's 0 or 2 or something like that. So take that 0.3333333 and add it to itself twice. Do you get 1 back? Nope, you get what? 0.9999999, right? Weird things happen with floating point numbers. So I would not recommend that you follow this pattern, especially with floating point numbers like doubles. Instead, be explicit about this. So if that's a greater rating, then they're in order, and I would return something negative. Else, always save that last equality test for the final condition here. Return, if they're equal, if they truly are equal, then it's going to be what? 0. Let's use this. We'll sort it again, print it out again, but we'll use this IMDb rating right here. And now we would expect all the best films at the top, 995, the worst films, 850. Now, I do agree on that relative ordering there, but it should be higher than 8.5. Right? If you haven't seen all these, go and watch them all. That's your Thanksgiving requirements, right? A question online here, couldn't you in theory return the ceiling function of the difference? Obviously it's still bad practice, but it gets rid of the integer truncation problem. Yes, you can, but not for negative numbers. For negative numbers, you end up needing to return the floor, right? So you don't want the ceiling or the floor, either one of those. What you want is this other mathematical idea called the signum, signum or signum. In other words, in some languages they support it like the signum. If you give this a -1, it'll return, or -1.5, it'll return -1, guaranteed to be -1 as an integer. If you give it 1.5, it'll be guaranteed to give you 1, even if you have 10.5. It returns the sign. So it returns either negative or positive, and I think that 0 is considered to be positive, or non-negative at least. Right? So what you want is the actual signum. Good question online. Right? One last thing that we could do, instead of ordering the directors by name, what else could we order them by? Their date of birth. So this date of birth comes before that date of birth if the year is less than, or this year, right? What if the years are the same? Then you have to go to the month. What if the months are the same? Then you have to go to the day. That seems pretty complicated, but you can do it, right? I would probably make a comparator for a date itself, and then pass that off to that function, right? But it's just, you know, a few extra lines of code, right? But we're not going to go through it because I believe everybody here could do it if they wanted to. Right? If not, then post on Piazza and we'll have a code jam. All right, questions so far? Then let's use everything we've covered so far to bring to bear on an actual problem. Now, this is not an actual problem, but this is something I use every year. I did not use it last year because of COVID. COVID ended the semester before Thanksgiving. But what I've typically done throughout the years for this course is, as a review, I'll either live stream or in class we'll do it, the Advent of Code problems. If you've not seen this, it's an excellent website that's been run for now, this will be the 6th year, I believe. We can find out here. Here are all the events. It started in 2015. It's an advent calendar of code. So if you're not familiar with it, advent calendar, you know, there are 25 days to the Christmas. And so on the first day, you have a certain number, you have for every day you have 2 exercises. The exercises usually build on each other. So if you do the first exercise hackishly, it makes the second exercise difficult, right? And of course, they proceed in difficulty throughout. This was in 2015. You can still access all the old ones if you want to and go back. You do need a GitHub account or something like that to log in. But otherwise, you can see here in 2015, I got all 50 stars. I did them all, right? Last year, I didn't bother doing them until at all because we didn't have a review. But typically what I'll do is I'll do like day 1 as a review, day 2 as a review. Again, they get more complicated as we go on. So what I want to do is, I just on a whim, maybe a week ago or so, I checked out the 2020 problems. And the very first one was excellent because it ties into exactly what we're talking about here, searching and sorting. So don't worry about the background. There's usually some stupid story to go along with this stuff. And you're collecting stars along the way. It's just programming exercises. What you need to do is focus on what the actual problem is here. So we need to find 2 entries in this file. And here, I'll show you what the file looks like right now. Right? Everybody gets a unique problem. And so when you log in, you get your input is not the same as somebody else's input, so there's no cheating there. But here's my input. Right? My input that year was, or for this problem, was just a bunch of numbers. Right? There are actually, I think, 200 numbers there. Okay? And I need to zoom back out here. So usually they give you a sample input here to show you what a solution looks like here. What you're trying to do is you're trying to find 2 numbers that sum up to 2020, the year in which it was offered. Right? So for example, 1,721, the first number here, and 299, that number right here, when you add those together, that's 2020, right? That equals to 2020. And then what the answer is you need to take those and you need to multiply them together to give the answer, and you enter the answer into the output. I've already done it, of course, so I'm not going to enter it again. But my answer was what? Here, 63,616. All right, let's go ahead and do this as an exercise, and then we'll come back. We don't need to do the second part here. I just want to focus on the first part. So we have a couple of examples here. We've got this input example, we've got my actual input example, and then yet another example that I'm going to show you here in a moment after we've done this first exercise. But remember that my answer was 63,616. We'll come back to it, okay? So let's go into exercise here. And let's go ahead and check out, there's my input right there. It's in a file, I just cut and pasted it into a file called day01.txt. Let's go ahead and start by creating a source file. Solution, say. And it's completely from scratch here. So I'll probably want to include the standard library. I'll probably want to include the standard input-output library. Maybe I want math, but probably not. We can always come back to that. Int main, int argc, char argv. And if you want, you can go ahead and jump into Advent of Code, go to 2020 day 1, and get your input and work on your input along with me while I do mine. All right? So my first task here is to process this file and get all those numbers into an array. I can tell you immediately that there are 200 elements in here. Right? So I'll just hard code that value. Int n is equal to 200. And I want to open the file and read each line, convert it to an integer, and store it in an array. Right? That's what I want to do as a first task. So help me out. What's the first thing I need to do? I need an array first of all, right? So ARR is equal to, how do I create an integer array of size 200? I need to typecast the return value from malloc, right? size of int, and you want 200 of them, so there you go. Right? All good. Basic error checking if you really want to. This is just a quick and dirty solution though. Right? Now I want to open the file. How do I do file IO? With a file pointer. How do I open a file? Open. And what file do I want to open? I called it day01.txt. I mean, for what purpose do you want to open it up for? Reading. There we go. Now, I already know exactly how many lines there are in here. If not, then I can reuse some of the functionality that in fact, when I did this, all I did was copied my hack 10 and I modified it because I have functions in there that read an entire file line by line. I've got a function in there that reads an entire file all as one big chunk, one big string, right? Reuse those. That's why we had you do them, by the way, so that you could use them in another part of the hack and use them in future hacks as well. All right, so back to the solution here. For int I equals 0, I is less than n, I plus plus, I will read one line. Where am I going to read that line into? I need a buffer. So char buffer. And how big should I make this? Well, each one is only 4 bytes, four digits, plus the end-line character, plus the null terminating character, 7, but there are going to be bigger numbers later on. So I'll just make this large, 100. Right? No wasted space there. A little bit of wasted space, but who cares? Right? All right, how do I read an entire line of a file? Do you remember, or do you forget? So, thank you. Thank you for laughing. Right. There, forgets what, and I do genuinely forgot the order of the things. So it looks like that's the buffer, the size, and then the stream, the file, right? So it's the buffer, the size of the buffer, 100. Remember that it will read at most 100 minus 1 characters because it takes care of that null terminating character for you. And you want to read from that input file F. Once I've got that in the buffer, by the way, I'm not capturing the return value here either because I know exactly how many lines there are because I already looked at the file. But in general, you would want to look at the file. How many lines are there? How many characters are there? Like you did in hack 10. Now I need to convert it to an integer. How do I convert what's stored in the buffer to an integer? A to I, good. A to I of the buffer. Oops. There we go. I've got my x. And now how do I store that into my array? Array sub I is equal to x. Great. I've opened the file, I've read each line, I've converted it to an integer, I've stored it in an array. Let's just go ahead and make sure, piecemeal testing here, ad hoc testing, make sure that I've got everything read in correctly. So for all those elements, go ahead and print it out. Printf %d and the line of array sub I. I'm not going to want to do this in general, but I will go ahead and make sure that it's actually reading from the file. Oops, get that out. There we go. 1778 is the last one. 1778 is the last one. 2000 was the first one. 2000 was the first one. Looks like it's working to me. Okay? All right, I'll go ahead and get rid of it. If I ever want to restore that, fine. I'll go ahead and put that, although ideally, what should I do? probably put that into a function called print array, or just steal a function that I've already written or that I've provided to you or something like that and reuse that function. But I'll go ahead and leave it there for now. Again, in general, don't do this because this is leaving dead code in there. It's leaving Cruft, right? Remember Cruft? That's the Cruft Hall at Harvard or whatever, or Yale, where they just threw their garbage. Don't leave garbage sitting around in your code. All right. Now what? I need to find the pair of numbers that sums to 2020, the year, last year, the year that it was offered. So let's run over all pairs. For int I equals 0, I is less than n, minus 1, I plus plus. And within that, for int j, starting at I plus 1, j is less than n, j plus plus. Now, how did I know to do that off the top of my head? That's what selection sort did, right? Selection sort went for I running from 0. It stopped short because once it had sorted the first n minus 1 of them, then the last one was where it needed to be. J starts at I plus 1 because if I'm looking at I don't want to compare it to everything that went before it. I want to compare it to everything that comes after it, right? And I take a sum, right? Int sum is equal to array sub I plus array sub j. Right? If I had started at here, I, is that correct? I plus the element at I plus the element at I, you could get 1,000 and then 1,010, 1,010, and that would be the wrong pair because it's not a pair. You're comparing it to you're matching it up with itself. Okay, plus 1. Also, the most common, not the most common, but in a couple of posts last night on Piazza, we saw one particular error that looked like that. You've got to be careful with your I's and your J's. This would cause it to seg fault. Why? Because it's going off, right? I is less than n. J would just keep on going because you're not changing I in this inner for loop. So eventually J falls off the edge of the array and you get a segmentation fault. So be careful. Make sure that you've got I, J, J, J. Okay. If my sum is equal to the target, to 2020, if sum is equal to 2020, then I have found the pair that I'm looking for. Now what I'm going to do is I'm going to put this into a variable up here because I'm going to change this later on for our own purposes. And so if that's equal to the target that you're looking for, right, then I will print out found the pair. That is %d, end the line. And this is my ARR sub I and ARR sub j. And I need a comma right there. There we go. Good question. I did this before, so there's not. But what if there were? Then you could report multiple pairs. Right? In fact, no, I won't end up reporting this pair twice. But let's find out. Right? There we go. Found the pair 32, 1988. So 32 times 1988 is going to be 63616. That looks familiar. 63616. I put that in, I got my star. All right. Okay. Well, they do not give you big, giant inputs. Sometimes they'll give you things that if you do things in advent of code is what I'm talking about. Sometimes they'll give you problems that if you don't solve it smartly, or in a smart manner, I guess, because smartly is not a word, or maybe it is. If you don't do it in a smart manner, then you will not get the answer. They do give you stuff that would take 11, 12, 20,000 years if you did it the naive way. I wanted to produce an input that if you did this solution, you would never find the actual solution. So let's go ahead and take a look at that. I'm not even going to be able to open it up here. What I did is I generated a bunch of random numbers. I can show you what it looks like. Big day one, right? I generated a bunch of random numbers such that the sum would add up to 2021, 2021, right? So in other words, the target is no longer 2020, it's now 2021, 2021. 21, whatever that is. That's 20,212,021. Right? How many of them are in here? That's a lot. I don't want to have to read that, go through all of them. In fact, I can't even open it up because it's too large. So I'm going to go ahead and do a word count. How many lines are in that file? 1 million. Right? So let me go ahead and change n to be 1 million. I shouldn't have used 200 anyway. I should have used n. Right? And I think that that's all good. Okay. So GCC this, run this, and we'll let it run for a little while here. Right? While that's running, let's think about what's actually happening here. Right? So selection sort, remember, makes about n squared comparisons. That's what I'm doing here. Right? Let's go to wolframalpha.com. So what I'm doing is I'm taking pairs. Now that you've done binomial coefficients, you understand how this works. Binomial coefficients says that if you take n elements and you want to choose k of them, there are this many ways of doing that. Right? So I've got 1 million elements, and I need to choose 2 of them to sum them up to see if that's the sum that I'm looking for. Right? So how many ways are there of doing that? 1 million, 1, 2, 3. Choose 2. Right? How many is that? A lot. Yep. That's 499 billion. So let's just say 500 billion. Right? We'll round it up there. Right? 500 billion. I'm doing 500 billion operations here. How long will this take? Very, very, very long. Right? In fact, let's just estimate that if I'm able to choose, or if I'm able to do, say, 1 million of these things per second. 1, 1, 2, 3, 1, 2, 3. Right? There we go. That's the number of seconds it'll take. So I don't know. Let's just go ahead and say that I have 10 times as powerful of a computer. Now it's 10 million operations per second here. Right? And that is going to be 60 seconds in a minute, 60 minutes in an hour. Is that manageable now? So 14 hours. So come back tomorrow. By the way, we can increase this by an order of magnitude. Again, 100 million operations per second, and it's still going to take us over almost an hour and a half. Right? I can tell you that this is not that performant of a Docker instance sitting on some Amazon Web Service somewhere. Right? So let's kill it, and let's rethink this. Yeah, what if I sorted it? Right? Well, first of all, before we determine what I could do if I sorted it, let's go ahead and think about how to sort it, first of all. These are all integers, right? So let me go ahead and go back to this demonstration that we had. I think I might have gotten rid of it. No, or search. Let's see. Did we have? Nope, I got rid of it. That's fine. We can rewrite it. So I want a comparator for integers. Int, CMP, int x and y. Is that what I want? Nope. What is a comparator again? Const void star a, const void star b. Right? And what is the first thing I need to do? I need to convert them to integers, well, integer pointers. Const int star x is equal to const int star of a. Const int star of y is equal to const int star of a, or b, sorry. And then if dereferencing of x is less than dereferencing of y, then I will return something negative. Else if dereferencing of x is greater than dereference of y, I'll return something positive. Otherwise, I'll return 0. There's my comparator for integers. If I were to use this and sort it before I started processing stuff, qsort of the array, how many things are in the array, n of them, and how many bytes does each one take, int, and I want to use that CMP int for comparisons. How could I exploit that? So consider x int x is equal to ARR sub I. Right? Let's suppose that it's that first element. In fact, let me go ahead and go more big. There we go. 33259178. If that had a match somewhere else in this list, big giant list of numbers that sum to 2021, what would it be? So 2021 minus that number would give me that number, right? Right? Yeah, there were no negative numbers, but that's okay, right? So what do I need to do? I need to search for this number right here. How does that help me to have sorted it? Int y is going to be the target minus x. Right? I need to search for y, ... If y exists, you found your match. So how do I search? What if I did a linear search? Right? Yeah, that's exactly what I was doing before, right? I was starting at the next, here's the element. Do any of these sum with this one sum up to the target, right? So I was just doing a linear search just on part of it. It was still a linear search though. Binary search, I heard. How does binary search help me on that? Because it's exponentially faster, right? Instead of linear search, order n number of comparisons, it ends up doing a logarithmic number of comparisons. So how do I use B search? Exact same way that I use Q sort, except that the first argument is different. Oh, by the way, an aside here. Remember, I think in lecture on Monday, I said, I don't know why B search needs the size of. And now I do remember why it needs the size of, right? It needs to know, so it needs to know where the middle is. How does it know how many bytes over the middle is if it starts over here, right? It needs to know that, oh, that's 10 elements away, so how many bytes over do I need to go? 10 times size of bytes in order to jump to that location, and that's why it needs it, right? Okay. Anyway, I thought about that the next day. Oh, of course it needs to know how many bytes there are in there. So the B search is I'm going to pass in y. Does y exist in the rest of the assorted array now? And again, I'm using the same comparator here. If I had used a different comparator, CMP, right? Is that guaranteed to find what I'm looking for? Nope. If you're going to search and sort, you need to use the same comparator. As you saw yesterday, you couldn't find cubs in the last exercise, or maybe it was the first exercise, I forget, because it was using a different comparator. Right? B search returns a generic void pointer result, which I will force to become an integer pointer. Right? Now it returns an actual pointer to the value if it finds it, otherwise it will return null. So if it returns null, then the no such element y exists. Right? All right, move on. If it does not return null, that's where I have found the one I'm looking for. Eureka? Is that how you spell it? Right? X and y, x plus y is equal to target. So how do I get that? Before I was going array of I plus array of j. I don't have a j here anymore, do I? But I have the memory address of it. So printf found %d, and the line. The first one is, of course, x. I guess, well, I could just print out y, I guess, right? There we go. But let's get some more practice here. Could I print out result? Result is a pointer. If you wanted to, you could go ahead and format it as a pointer. But how do I change a pointer into a regular old variable so that I can print out its contents? Dereference it, star. GCC. All right, remember, we estimated that it would take at least 1.5 hours. Ah, darn it. I did 2021, right? All right, fine. I screwed up here somewhere. target minus x. I had the solution before. So if it's not null, we print it out. Okay. Darn it. Well, we didn't get the right answer, but at least we didn't get the right answer quickly. Right? I'm not sure what I did wrong here. Oh, sorry, wait. It is in the, inside the for loop because I want for each element here. I did sort it. I did that. Darn it. Up here. Right. 20, 21, 21. All right. Say what? Oh, thank you. Duh. It's big day. What is it called? Big underscore day. There we go. Right. Of course, it's not going to find any numbers in that small little file that sum up to 20 million something, right? So let's go ahead and compile this again, and let's run it. There. Oh, wow. Okay, actually, there are two of them. Apparently, I had duplicates, so it ended up reporting both of them. The way that I originally did this is once I found it, I said, okay, I'm done. Exit. With no error code and be done with it. Right. That's okay. There are two of them. Actually, if they're not two of them, what's going on here? With the other loop, what I did is I only went from, if I've got I only looked at things after it, never before it. If I had looked at things before it, then this one and this one matching would have appeared twice because it matches when I look at this one first and then this one second, and then this one second, and then this one first. That's what I'm doing here with this binary search, right? I'm going through, all right, for this one, search for the other one, found it. Now for this one, search for the other one, and you found it again. And that's why in my original I had exit. Once you find it, you're done, right? Go ahead and stop the entire program here. Right? And I'll go ahead and restore that there and then run it. And 1.5 hours or 13 hours or days, right? Versus an immediate answer here. Which one's better? The immediate answer, right? Unless you're paying by you're getting paid by the hour or something, right? Let's verify. In fact, that is 2021, 2021. I had to make it that big because you would run out of, if I only made it like 2021, then you would run out of numbers, possible numbers pretty quick. I couldn't have a million numbers because there would be a lot of repeats there. And with a lot of repeats, you would get lucky and you would find them right away. Right? This one I made sure that there was only one pair that worked and that there were a lot of pairs that didn't, 1 million of them. You will see this in your project. In your project, what you're going to be doing, well, first of all, in Hack 14, you'll be laying the groundwork for your project where you are going to come up with a model for this transaction. This financial data where you've got an account that has a certain balance and then a transaction, transferring money from one account to another account or from that a different account to this account. I think that they're all, there are several different transactions. Some of them are deposits, some of them are debits, so like when you pay for a credit card or something. And what we did was we took, I found this data set that was generated artificially, so it's not actual real financial data. I went through it and massaged it a little bit, came up with what I wanted, and you are going to be doing several reports on this data. For example, you are going to be taking one data set and another data set that say 10 million transactions and 10 million transactions, and you need to go through and find out which transactions are anomalous. Oh, this transaction from account A to account B was for $10, but in this data set over here, it was from account A to account B for $11. Suspicious, right? Report that. You'll need to report everything that that is more than $10,000 transaction because that's a red flag to the IRS. You need to report everything that is, you do some, I forget what it's called now, but you do some analysis. What is it? Benford analysis, that's it. You may not be aware of it, but real data follows a probability distribution based on the first digit. It's not uniform. So what's the most common first digit in any real piece of data? 1, followed by 2, and the least common is going to be 9. Right? And you can basically, what you can do is you can use Benford analysis to say that that data is suspect because it looks like it was artificially generated, that it was uniformly generated, rather than this real data over here that follows a Benford distribution. Right? So you'll be doing several examples like this, and it's all explained in the project. Remember that there is no collaboration for the project. You can collaborate, and you should collaborate on Hack 14 to lay the groundwork for the project. But after that, everything will be a show of your searching and sorting skills, as well as your file I/O skills, your string manipulation and processing skills, etc. Right? So, question, and again, if you do things naively, like my first attempt over here at solving this problem, it ain't gonna run. You need to use searching. You need to use sorting. You need to think about it, from an algorithmic point of view. Okay. Any questions? No? Part 2, by the way, was just finding triples instead. Imagine how much worse that'll be. 1 million times 1 million, naively, was 500 billion. Times 100 million, times a million more. What's that going to be? Billion, trillion, quadrillion? 500 quadrillion? Is that right? Yeah. Now you're getting into probably years instead of hours. All right. Again, if it's adventofcode.com. If you want, the most common question we get towards the end of the semester is, how could I prepare for the midterm, or how could I keep up with stuff over the break? Pick up a new programming language and do the advent of code. You can go back. Now again, this is the 6th year or so. Right? 1, 2, 3, 4, 5, 6. This will be the 7th year. It started in 2015, and lots of fun little exercises here. Okay. All right. I'll see you after the break.